Welcome to this scientific lecture on the parallelization paradox in microfluidic systems. Today we'll explore a fascinating problem where our experimental speed outpaces our ability to analyze the results. Imagine you have the ability to read 1,000,000 books simultaneously, but you can only turn one page at a time. This is the essence of the parallelization paradox. Modern microfluidic systems allow us to run millions of picoliter-scale droplet experiments simultaneously. Each droplet acts as an independent microreactor. However, the massive amount of data generated overwhelms any classical analysis pipeline. The bottleneck shifts from experimentation to data analysis. First, let's understand the scale we're working with. What exactly is a picoliter? 1 picoliter equals 10 to the negative 12 liters. That's incredibly small. To put this in perspective, 1 picoliter is about 1,000th of a cubic micrometer. A typical picoliter droplet might have a diameter of about 10 micrometers. That's smaller than many biological cells. Now here's where things get interesting. How many of these tiny droplets can we generate and process? Modern microfluidic systems can generate about 10,000 droplets per second. That's an impressive rate. In just 1 hour of operation, we generate 3.6 times 10 to the 7th droplets. That's 36 million individual experiments. Each of these droplets acts as an independent chemical reactor, where reactions occur in isolation. Let's compare this to traditional laboratory methods. How do picoliter droplets stack up against conventional reactors? A traditional 1 milliliter reactor performs one experiment at a time. But the same volume and droplet form could contain 1,000,000 picoliter droplets, each running a separate experiment. Mathematically, 1 milliliter divided by 1 picoliter equals 10 to the 9th. You could fit 1,000,000,000 picoliter droplets in 1 milliliter of volume. This represents a billion-fold advantage in the number of experiments you can run in the same physical volume. But volume isn't the only advantage. Let's talk about speed. Small droplets have unique kinetic advantages. The surface area to volume ratio increases dramatically as size decreases. This affects heat transfer and mixing. For a sphere, the surface area to volume ratio equals 3 divided by the radius. Smaller radius means higher ratio. For a 5 micrometer radius droplet, this ratio is 6 times 10 to the 5th per meter. That's enormous compared to bulk reactions. Diffusion distances are tiny, so molecules mix and equilibrate much faster than in large reactors. Diffusion time scales as length squared divided by the diffusion coefficient. For a typical small molecule with diffusion coefficient of 10 to the negative 9 square meters per second in a 10 micrometer droplet, the diffusion time is only about 0.1 seconds. Mixing is nearly instantaneous. Now we arrive at the heart of the paradox. All these advantages create a massive data problem. Each droplet is typically monitored using optical methods. As droplets flow past detectors, they generate fluorescence or absorbance signals. Each droplet might generate 100 to 1,000 data points depending on the temporal resolution and measurement parameters. With 10 million droplets per hour and 1,000 data points each, we're generating 10 billion data points every hour. Now let's examine why classical analysis methods fail to keep up. A human scientist manually analyzing data might examine 1 droplet per minute at best. That's generous. That's 60 droplets per hour for a human working continuously. The ratio is 10 million generated divided by 60 analyzed, which equals about 170,000. The system is 170,000 times faster than the analyst. Visually, the generation capacity vastly exceeds our analysis capacity. This creates an enormous gap. Let me give you a powerful analogy to understand this paradox. Suppose you had a magical ability to read 1,000,000 books at the exact same moment. All the information enters your mind in parallel. However, you're still limited by the physical constraint that you can only turn 1 page per second with your hands. The books would all be finished and closed before you could even begin to process the first chapter. Your reading speed is bottlenecked by page turning, not comprehension. This is precisely what happens in microfluidic systems. We can run millions of experiments faster than we can analyze even one. You might ask, can't computers solve this problem? Let's explore computational approaches. Certainly, Modern computers can process data much faster than humans. Automated image analysis can examine thousands of droplets per second. A good computational pipeline might analyze 1,000 to 10,000 droplets per second. At 10,000 per second, in 1 hour, we can analyze 3.6 times 10 to the 7th droplets. That matches the generation rate. So you might think computers have solved the problem. But there's a deeper issue. Keeping up with data generation is not the same as understanding the results. Computers can detect signals and classify droplets into categories, but extracting scientific insight requires human interpretation. When you have 10 million experiments, you need entirely new frameworks to recognize meaningful patterns and correlations. With massive datasets, statistical significance becomes both easier to achieve and harder to interpret meaningfully. The p-value typically scales as 1 over the square root of the sample size n. With huge n, tiny effects become statistically significant. With n equals 10 million, even trivial effects can have p-values around 3 times 10 to the negative 4. This is where machine learning enters the picture. Can I solve the parallelization paradox? Neural networks excel at finding patterns in high-dimensional data. They can learn to classify droplets based on complex feature combinations. Convolutional neural networks can process raw optical images of droplets, extracting features automatically. Recurrent neural networks can analyze the time series signals generated as each droplet passes through the detector. However, training these networks requires 100 to 1,000 GPU hours. That's substantial computational investment. Machine learning introduces its own version of the paradox. The models can make predictions, but understanding why becomes opaque. Let's not forget about data storage. Where do we keep all this information? Suppose each droplet's complete dataset requires about 10 kilobytes of storage. 10 million droplets times 10 kilobytes equals 100 gigabytes per hour. Running continuously for 1 week generates 16.8 terabytes of data. At typical cloud storage rates of 2 cents per gigabyte per month, this becomes expensive quickly. 16,800 gigabytes times 2 cents equals $336 per month just for storage. There's also a fundamental mathematical challenge called the curse of dimensionality. Each droplet isn't characterized by a single number. We measure fluorescence intensity, size, velocity, temperature, and more. Typically, each droplet has 10 to 50 measured parameters. That's 10 to 50 dimensions in parameter space. The volume of parameter space scales as r to the power of d, where d is the number of dimensions. With 10 dimensions, doubling the search radius increases the volume by 2 to the 10th power, which is 1,024 times. Even 10 million data points become sparse when spread across a high-dimensional parameter space. Let me give you a concrete example from pharmaceutical research. Imagine screening drug candidates to find which compounds bind to a disease target protein. A typical drug library contains 1 million compounds to test. At 10,000 droplets per second, you could test the entire library in just 100 seconds. That's less than 2 minutes to screen 1 million compounds. Remarkable speed. However, identifying which signals represent true binding events versus artifacts requires careful analysis of each positive hit. Even with a false positive rate of just 0.1%, you'd have 1,000 candidates requiring follow-up validation. So how do we actually solve the parallelization paradox? The answer lies in hybrid strategies. Strategy 1 is hierarchical analysis. Use fast automated methods to filter data, then apply detailed analysis only to interesting subsets. Automated screening eliminates 99% of droplets as uninteresting. This reduces the dataset by 2 orders of magnitude. 10 million times 0.01 equals 100,000 droplets, requiring detailed human or intensive computational analysis. Strategy 2 is adaptive experimentation. Use real-time analysis to guide subsequent experiments. The first few thousand droplets provide initial insights that help focus the remaining experiments on promising parameter regions. Strategy 3 is dimensionality reduction. Use techniques like principal component analysis to project high-dimensional data into interpretable, lower-dimensional spaces. Reduce from 50 dimensions down to 2 or 3 principal components that capture most of the variance. Ultimately, the parallelization paradox reveals a fundamental trade-off in modern science. There's an inherent trade-off between how fast we can generate data and how deeply we can understand it. We can either explore vast parameter spaces broadly or examine specific phenomena with great depth, but not both simultaneously at maximum capacity. Classical methods provide depth but limited breadth. Droplet methods provide enormous breadth but challenge our depth of understanding. The frontier is moving along this trade-off curve. What does this mean for the future of scientific research? The traditional hypothesis-driven scientific method needs to adapt to handle massive parallel experimentation. Scientific discovery increasingly means recognizing meaningful patterns in enormous datasets rather than testing individual hypotheses. The future requires deep collaboration between human insight and artificial intelligence to extract meaning from data. Let me summarize the paradox with key numbers. We can generate 10 million droplets per hour. Humans can analyze 60 droplets per hour. Computers can keep pace at 3.6 times 10 to the 7th per hour. But truly deep understanding, extracting mechanistic insights, might only be possible for 10 droplets per hour. The true paradox ratio is 10 million divided by 10, which equals 1 million. The system is 1,000,000 times faster than deep understanding. This is the essence of the paradox. The experimental system operates faster than the scientist can observe and comprehend its output. Where do we go from here? What are the promising directions to resolve this paradox? We need machine learning approaches that not only make predictions, but explain their reasoning in scientifically meaningful terms. New visualization techniques that can represent millions of data points and tens of dimensions simultaneously. Closed-loop experimental systems where analysis directly feeds back to control subsequent experiments autonomously. Fundamentally, we need to train the next generation of scientists in both traditional scientific methods and modern data science. The parallelization paradox raises deep philosophical questions about the nature of scientific knowledge. When a machine learning model correctly predicts outcomes for 1,000,000 experiments, does that constitute understanding? Can we accept statistical correlations as scientific knowledge even without detailed mechanistic explanations? When an algorithm discovers a pattern in massive data, how do we validate that discovery using traditional scientific methods? The parallelization paradox isn't a problem to be solved, but a new reality to embrace. The ability to run millions of experiments simultaneously has permanently transformed how we do science. We cannot return to the old paradigm of testing one hypothesis at a time. The cat is out of the bag. Moving forward requires developing new analytical tools, new experimental methods, and fundamentally new ways of thinking about scientific discovery. The future of science belongs to those who can transform massive parallel data streams into genuine scientific insight and understanding.